Okay, in our part B of this example, V2.1, we're going to look at a T cross-section. Last time we looked at rectangular one in part A, and now we're going to look at one that's arranged like a capital T. Same total amount of cross-sectional area. The one we had before was 6 inches high by 4 inches wide as a rectangle, 24 square inches. This one also is 24 square inches. We got a 6 by 2 piece here and another 6 by 2 piece here. And we're going to see the impact of rearranging the material, even though it has the same amount of materials in a different arrangement. Right? So we're given the amount of transverse shear, and we want to figure out what the shear is at one particular point, point B, as well as the variation across the cross section, which I've already begun to summarize over here to the right. Right? Now, we might choose point B here because of this sudden discontinuity we have between this upper portion, the flange of the T, and the stem of the T. And that's going to cause us here to have multiple answers here, 3 actually, instead of just 2 that we had back in the other one, part A for the rectangle. Right? So we'll see how this all begins to play out. Now, number 1, we got to get the second moment of area property information. We got to know, to do that, we got to find the centroid. Right? And so it's not so obvious where the centroid is located here, at least up and down. Right? So I decided to measure things from the bottom when I did my first moment of area calculation to locate that centroidal axis. Right? So the wide bar bottom, from the bottom was my reference, was the sum of the first moments of area of these little pieces with respect to that bottom divided by the total amount of area, which I've already said is 24 square inches, and there's the proof of that, right? So I do the bottom piece here and then the top piece, right? The 3 inches is the centroidal distance to this rectangular piece here from the bottom. And so that 3 times the 6 times the 2 plus then the moment arm for the second piece times its area. The second piece is this 2 by 6. That's up here at 6 inches plus the 1 to get to its centroid, again, measured from the bottom, and you come up with the composite, or a centroid of the whole thing is at 5 inches, and that's the location of the neutral axis. Right? Then we got to find the second moment of area of this piece. Now you got to apply the parallel axis theorem to do that. Right? So we have rectangles in both pieces, so 1/12 of the base times the height cubed plus the area, 2 by 6, times its distance squared. Right? So moving from its local centroidal location to the global that we want, which turns out to be 2 inches, right? The 5 minus that 3 from the bottom gives us that distance movement term, right? Same thing for the top piece, right? 1/12 the base times the height cubed, plus then that area of that piece times its movement, which is 1 inch up to this bottom piece, and then 1 inch up into the piece itself. So that's where the 2 inches comes from. Not directly this 2, but rather a 1 and a 1 to get us that 2. Total thing is 136 inches to the 4th. Before, when it was a 6 by 4 solid rectangle, that was only 72 inches to the 4th. So we have increased this, not quite 100%, but nearly 100% just by rearranging this, made the section stiffer and stronger from the standpoint of stresses and stiffness. Right? So as we look at that overall now, that's a lot, right? That's just the geometric properties, just so that we can now find the transverse shear stress at point B caused by this transverse shear force, right? So let's go find the Q, capital Q, that goes in that calculation, right? So that will be this upper portion here. There's your capital Q. It is 6 inches wide by 2 inches high. That's the area, right? Now, its moment arm is with respect to our centroidal or our neutral axis. So that's that distance right here. So that'll go up 1 to get to the bottom of that rectangle, and then another inch. Oh, it turns out, in this case, it was the same as this movement term down here in the second moment of area. Right? So there's that 2 inches. Just this quinky-dinky for the math that we've been working, right? So I'll put that down below. So that Q is going to be 6 times 2 times 2 is going to be 24 cubic inches. Since we're also going to find the shear stress of the neutral axis, let's go find the Q that's associated with that. Right? So that's going to be the first moment of this top area plus the first moment of this little area that's left over, which will be then that 24 that we just found, plus then this little area, which is 1 inch high, is left over, times our 2 inches wide, times then its centroidal distance down to the big centroidal centroid. So that's a 1/2 inch, or that's just going to be all of 1. So that will be 25 cubic inches. Now, interestingly, that should be the same value if we had chosen to use this bottom piece down here, right? So that would be 5 times 2, that'd be 10 square inches down here, times its moment arm, which would be 2.5, that would be 25 cubic inches too. You can go either way here to get to the Q. So it's just the critical part is the first moment of the area outside of the point of interest. We're now at the neutral axis of all of this area. That first moment will be the same as that. Now the areas will not be the same, right? We don't divide the areas into 2. That's actually plastic behavior. That's not what we're doing here, right? So this is the geometric centroid business and this first moment of area business, and more than one way to go skin the cat, so to speak here. I don't know why people want to skin cats. Cats are lovely animals, just like dogs are. So no skinning the cat, but we got more than one way to get those numbers. Those are the Qs. Getting ready then for the tau equal VQ over ID business. So let's now then calculate our tau. Right? So let's do this in stages. I'm actually going to start at the neutral axis first. That's kind of weird since I set it up the other way, but you'll see why. Okay, you don't want me to do it that way. All right, we'll do it at B first. And you'll see why I was hesitating. I didn't really want to do that. All right, so applying VQ over IB. Right now, here's where the wrinkle is. And that is these parameters vary depending on where we're looking at here at this interface. Right now, which ones vary? Well, the V doesn't. That's still 50 kips. Right? The Q doesn't. That's the 24 cubic inches. The I doesn't change. That's for the whole cross section. That's 136 inches to the 4th. It's the B that changes. Right? So if we're looking at the transverse shear stress that's in the stem, then the B is 2 inches. All right, so that's tau B in the stem. If we're in the flange, so just below, we're in the stem, just above, all of a sudden this width jumps up to 6 inches. Everything else here is the same. We get the 50 times the 24 over the 136, but now that B value is 6 inches. So there's going to be a factor of 3 difference here, and it's going to go down as soon as we get it up into the bigger area. And so those numbers, then let's see what that would be. And I'm going to have to turn on the light here to get my solar power calculator to work right. Right, so we got 50 times 24 divided by 136. That's the part that stays the same. And then divide by 2 on the first one. And we have 4.41 for that one. KSI. Right? The second one will be a third of that. Right? Because the only thing we changed was a 2 and the 6 and the 2a6 in the denominator. So that's 1.47. Right, so up here in this variation that I drew, then the lower value is the 1.47, the larger one is the 4.41. We have this immediate discontinuity that happens because the only thing that changes just a little bit above and below is that value of B. Okay, so that's for those two. For the neutral axis, it is of course, similar calculation. The only thing that's changing are the Q and the B values, right? The B and the I doesn't change. So now let's go for there. And taut, the neutral axis, 50 kips times our Q value that we determined for that is 25 cubic inches for the neutral axis, divided by the I value of 136 inches to the fourth, and then the B at the neutral axis, which is right here at the centroid, well, that was the 2 inches. Right? So this is going to be real close to taut B in the stem. Not going to vary a whole lot, but it will vary just slightly. 50 times 25 divided by the 136 divided by 2, 4.5955, or really about 4.6 KSI. Right? And so that would be the maximum. And the distances that we're talking about here, that would be 5 inches off of the bottom. And then we got another 1 inch here. You probably noticed you got a glare there. That's why this whole thing is there to begin with, right? So that's a 1 inch, and then we have 2 inches up to the top. And again, this is second order variation. 0 at the outer and maximum here at the neutral axis. Notice this is a big change from what we had in the first go around. As a rectangle, we had a maximum shear stress of the neutral axis of 3.13. Here we actually had a maximum shear stress of 4.6. It actually went up, even though we rearranged the properties. And you're like, well, wait a minute, I changed the properties and the applied stress went up. I don't want that. Well, here's the thing. In most typical beams, they're going to be dominated from a strength standpoint on the normal stress and not the shear stress, right? If this was all about shear stress, then we probably wouldn't be designing our beams to look like this. It might look like something different, right? But when typically the first thing that we have problems with in beams from a strength standpoint is related to the normal stress as opposed to the shear stress. And so we'll design for the normal stress, and then we'll come back and check to make sure that the shear stress maximums and variations are acceptable. And usually we'll be okay, except for in certain special situations, which you'll get into later. But essentially, the shorter the beam or the closer a point load is to the end of a beam where a support might be located, then that's where you tend to have other things that may control the design of the beam. And one thing we haven't talked about at all is the stiffness of the beam, which in certain cases will be more important than the strength of the beam. Right? A lot of different things that can go wrong in our members, and we'll explore some of those as we go along in other lessons.